तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we discussed some of the preliminary aspects of metal semiconductor contacts in a general way without referring to silicon or gallium arsenide or indium phosphide, because the basic theory holds good for all of them. So, we were trying to see also what will form ohmic contact, what will form rectifying contact. I just quickly go through some of them, because I want to build from there today. Okay. So, what we will do is take case by case. Okay. We will take the n type material, this already I have discussed yesterday, but few things I want to point out there by drawing this diagram. So, what we try to do is metal semiconductor contacts with that general heading, we take n type semiconductor, which we have done, but some aspects I want to and phi m greater than phi s. So, if you just draw once again, I will draw the diagram. You have the 0 level, okay, that is the 0 level. Now, a metal is there in this portion, that is EFM. You already will have some of the things in the previous slides if you take a look at, but this will make things much clearer now. So, that is the EFM, and what we are talking of is a situation where the phi m is greater than phi s. We have defined all these terms, that is phi m, that is greater than phi s. So, that would mean that the Fermi level here is above this in the semiconductor, that is phi m, this is phi f s. Okay. Now, if we are talking of n type semiconductor, the conduction band is here, that is EC, and the valence band is somewhere here, EV, and this is actually that electron affinity that we defined yesterday or in the previous lecture, energy between the conduction band and the neutral level, this level, 0 level. Now, the point that we mentioned yesterday is, now notice this difference is phi m, let me make the symbol consistent, phi m minus phi s. The Fermi level is above this Fermi level, the electrons are occupying at higher energy compared to this here. So, those electrons will, once you join them together, okay, the electrons from the semiconductor will get transported onto the metal till these are equalized. So, when that happens, you have negative charge built up on the metal, leaving positive charge behind the semiconductor. When you have negative charge in the metal, there will not be any space charge layer, because what you are dumping into the metal is very small compared to what you have in the metal, the electrons. So, you will have on the surface a charge sheet will be there, which is which is more than what it is usually, n plus delta n, that sort of thing, okay, on this side. So, there is no potential drop appearing across this. So, when a charge is removed from here, there will be potential drop appearing across this. So, as far as this diagram is concerned, this portion of diagram is concerned, there will not be any change. Whatever happens is happening on this side. That is what I wanted to point out today. So, okay. So, contact made between metal and semiconductor. Okay. This is a metal and this is a semiconductor. You make the contact. So, now as I mentioned, the electrons will get transferred onto this. So, on the left hand side, I will draw this position corresponding to the same level, same 0 level. I am not changing anything on left hand side, because nothing happens there, because the electrons that you put are small numbers. So, that is the 0 level, and this position also is the same thing, EF. EFM becomes equal to EF. So, what I do is I draw this continuously. So, what has happened is this Fermi level has come down, because electrons have got transferred from that semiconductor to the metal, leaving plus charges. Okay. Why do the energy levels go down now? See, whenever you have removed electrons from there, it is positively charged, and if it becomes easy for transporting electrons from infinity to that point. Plus charges are there, you can easily move. If a point is negatively charged, it becomes difficult to take the electrons because it will repel it, so you have to spend more energy. So, the very fact that you have removed electrons from here and pushed on to the other side, you left that side positively charged. Okay. It becomes easy to take electrons to that levels. That means, all the levels in that region have gone down in energy. That is the whole key to the thing, which I did not mention to you in the previous lecture, because I kept it for today for a detailed discussion. Because yesterday I gave you an overall picture, today we will get into details. So, that is why this Fermi level has come down, and with that all the levels will have come down. And you also note far away, that means you have this neutral region. So, I will draw this diagram here. That is the metal whose work function is greater than this phi of s, and this is the n type semiconductor, let it be silicon, gallium arsenide, whatever it is, and here I have made the contact. And this side, electrons have moved on to that side, leaving positive charges, uncovering these dopants. Negative charges are here. So, there is field from here to here. Electrostatic potential has gone up, energy levels have gone down because electrons have been removed. It becomes easy to take electrons, and then, so you have a potential variation from here to here. See, this energy level here has gone down, all the levels have gone down, and there is a potential variation from here to here, which would mean the energy level will bend like that depending upon the potential. So, up to that point you have this variation, up to that point. From that point onwards, it is flat. So, this is 0 level. So, 0 level has shifted down. You can see the 0 level energy itself has gone down, because electrons have been removed from there. So, it becomes easy to take electrons from infinity to that point compared to that. Okay. So, that is the thing, and from here to here it has to spend more energy to go there. Okay. Now, what about this Fermi level? You draw it only up to that point. In this portion you do not do, because it is not equilibrium situation there. So, you stop there and call it as the, oh I am sorry, this is the conduction band. Conduction band, you draw all the way up to this point flat, from that point onwards like this. So, that is the conduction band edge there, and the Fermi level now you do not draw here, you stop there, it is okay, because you talk now of the quasi Fermi level here. In the sense, it is Fermi level is the neutral region. If you use that, it will get, it will give you the electron concentration. that is the idea. Still you can use the Fermi-Dirac statistics to find the carrier concentration here. Now, then over here you have the valence band, but it works out better to see that diagram being drawn rather than see it in the slide at one flash. Okay, and that will move parallel to that. So, you have the situation like this. Of course, you draw it like this just to show that it is the boundary of the energy band diagram surface. So, now this is where this diagram is. This diagram what you see here is at that situation. Okay. Now, I will just remove this because there is no space there. The top portion I will remove now, because I can just now you understand this diagram has been obtained under thermal equilibrium condition there, nothing applied. So, I will just remove that just to show whatever is put there, okay, from here to here. Whatever energy distribution is present here, that is energy distribution. Fermi-Dirac statistics, levels are present all through in this metal in large numbers. So, I just draw the Fermi-Dirac function itself that will give that. It does not go to 0 there, and here this will be the distribution. All that has happened is, okay, these levels have equalized such that the tip of this and this matches. Okay, that is what is shown here. The tip is matching there, and you can see the barrier here, that I can refer to the whole thing now to this diagram itself. You can see this is the barrier which you call it as phi Bn, barrier for electrons. So, the electrons which are above this can cross that, and the electrons which are above this can cross that. So, what has happened is the Fermi level when it adjusts, number of electrons which are there above that barrier on the left hand side is equal to number of electrons on the right hand side, the matches. That is why the current is 0. Okay. Now, so the main point that I wanted to point out was this: I have not shifted anything here, I have shifted whole thing down with the variation there. Okay. Now, let us go to the case where you forward bias it, reverse bias it. Now, notice also this potential is like this, plus minus. Now, when I apply a reverse bias to this junction, I think I will, I think I could have retained the diagram, sorry. So, let me redraw that here, keep it. So, the metal and semiconductor, because this diagram comes only here. So, now if I apply a reverse bias, this is thermal equilibrium conditions. Okay. The voltage can appear only at this across this, because in the metal if there is a voltage there is large current flow, well electron concentration is very large. So, it is not going to appear across that, it is going to appear across this portion. It is like two resistors in series or one resistor and one insulator in series. If you apply the voltage, it will not appear across the conductor, it will go into the insulator. This is the insulator, it goes, but hold that extra voltage, extra charges must come up. So, this depletion layer will widen, uncovering extra charges, and that widens, and what happens to the potential at this point, energy level at this point goes down further, because you have removed more electrons from there, the energy of those levels will go down further. So, that is why you get the entire thing shifted down there. So, you have got, you can just watch carefully, that was up there going down. So, this whole curve now comes down. Let me just draw that with another color if it is visible. So, that is the way it goes. Main focus is on here. Now, this has shifted down with the same distribution coming like that. That is what is drawn there. Same distribution is there, it has shifted down. But you notice what has happened is the tip in the previous case was oh I am sorry, the tip in this case, I just made a mistake there, just redraw that. The tip in this case was slightly above that, in the slide it is there, okay. That is the one, and tip in this case is actually slightly above that, I think that is why. So, whatever is here, that is crossing and that is crossing here. I am sorry, this diagram has to be re-looked here. Distribution is slightly above that, but it is matched by the electron flow from that side. But in the previous diagram it is there, slide it is already there, just put it here wrongly. So, that is the thing. Now, when this level goes down with this reverse bias, that is made it more positive, V r, this will go down by an amount equal to V r. So, this entire E c will go down by V r. So, whatever tip was here above this, that has moved down below that. So, you can see here now, going back to this point, see this is the top of the barrier. On the left hand side, that whatever was above that originally, that has not changed. On the right hand side, originally it was coming right up to this point, above this, it has gone below. So, the electrons on the right hand side are not able to cross. So, when you reverse bias, the current is due to whatever was above that. So, this has gone, that has gone now, okay, and that is a picture. So, only these are giving rise to current flow. So, but again to point out what has happened is, under reverse bias condition or thermal equilibrium or forward bias, this barrier is not changing. So, number of electrons which can cross from the metal to the semiconductor is never changing, that is giving, that is I naught, current due to that is I naught, that is not changing. What has changed is, this has moved down, the number which is crossing from right to left is gone down to 0, because they are not able to cross. That is what I want to point out. So, how many can cross, that is reverse bias current now will be in this direction due to transport of electrons from left to right, that is from right to left, actual current flow. Actual current flow is from right to left, transport of electrons is from left to right. So, how many electrons are able to cross depends upon how much is this energy above this, that portion, okay. That portion whatever is above that, that will tell you how much electrons are flowing. How much is above that depends upon how much is that minus that. Okay. If this barrier is smaller, you will have more electrons. So, if the barrier is smaller, I naught will be more, this I is equal to I naught in this case, that will be more if the barrier is less. That means, if the barrier is less, the reverse leakage current will be large. Smaller the barrier, larger will be the reverse leakage current. Larger the reverse leakage current, closer it will be to the ohmic contact. So, the key is that, and that happens, okay. If this now here one more point that I want to point out is, what is this phi m minus phi of s? The phi m minus phi of s in the thermal equilibrium situation, that quantity will be built in potential. The potential built in will be, the energy band diagram has come down that much, that means that will be the potential that will be present originally there. Okay. So, this quantity when you apply reverse bias, this also will come down by the same amount, originally it was there. So, that is V r. Okay, all that, because that 0 level I have not shown here, that is why I just put that also down. Okay. So, now the key thing is the barrier height should be, you should be able to control, and barrier height you can control by adjusting this difference. More the difference, more will be barrier height, more will be built in potential. Okay. Just quickly run through that forward bias case. I do not have to redraw that. When you forward bias, the entire thing has shifted up from thermal equilibrium situation, and notice here, because the when you forward bias, so this conduction band goes up, Fermi level has gone up from the thermal equilibrium situation by an amount equal to the built in potential applied voltage. Okay. Is that clear enough? So, that I can just, so this is the original Fermi level which was parallel to that thermal equilibrium. Now, because the applied voltage is V and which is positive in the direction, in this direction, opposing the built in potential, you are increasing the energy levels in this portion, the whole thing goes up. Okay. So, the difference between this level and this level is the applied voltage. Now, once that goes up, the distribution remains the same thing. Okay. So, originally when thermal equilibrium condition was there, that was the limit. The tip was actually matching with that. Now, the tip has gone above that level. Okay. Is it all right? I will just draw that for clarity. When I draw forward bias, so once we go through this diagram, then it becomes very simple. Now, what we did is, from thermal equilibrium situation, which was like that, we have reduced the voltage by applying a forward bias. So, in this situation, this has not changed, that remains the same thing, that level is remaining same thing, because nothing is happening at that level. In fact, the barrier height doesn't change, that remains the same thing, because barrier height is dependent upon this edge, conduction band edge and the Fermi level. So, thermal equilibrium situation, if you had like that, okay, and then if you had this thing like this, those were the ones which were letting the electrons flow, and on this side redrawing the thermal equilibrium, it was like that originally. Now, when I apply a forward bias V here, this shifts up. Okay. So, this I can draw with that color, just slightly I am drawing, and corresponding to that you will have this distribution like that. Originally you had these electrons which are capable of crossing that side, and correspondingly you had these electrons which are capable of crossing. Now, you have these extra electrons, total number of electrons here. In fact, the integral when you go from here to here, those electrons are more than this number. So, this give rise to extra current in that direction. So, that is the thing which we have marked as ISM and IMS. IMS is actually current due to electrons injected from metal to semiconductor, that is in the direction, that is I naught. The ISM is current due to electron injection from semiconductor to the metal, okay, that way, that is current is from metal to semiconductor. So, that is the one which gives rise to this extra electrons give rise to current in that direction. So, that is why we have got now actually the current equal to ISM minus IMS. This I have gone through in detail last time, but some of these things which might not have been very clear, now with this diagram I think it is much better. So, why those energy band diagrams move up and down, those things, and also these extra electrons which are present giving rise to current in that direction. So, ultimately you have got that current I is equal to I naught into e to the power of V by V t minus 1, that is due to electrons. First term is due to the electrons from the semiconductor to the metal, and second term minus sign is due to the electrons from the metal to the semiconductor. So, okay. So, this is actually current due to the semiconductor to the metal minus current due to the metal to the semiconductor, and this is the first term, that is I naught, that does not change, this one all the time is I naught. Okay. So, the point that I was trying to point out is ultimately you can use the same equation. If you drop this down 0, how do you drop this down to 0? By making V is minus V r, reverse bias. So, that becomes minus I naught, telling you that if I reverse this polarity, whatever current was there will be in opposite direction with only the second term, metal to semiconductor. Okay. So, these are some of the aspects which make it clearer, and now again I am re-showing once more this characteristic, that characteristic, the diode characteristic is, after all, it is a diode, and a good diode and a bad diode. A good diode is rectifying diode, a bad diode closer to the ohmic contact, that is all what we are trying to tell, and a bad diode a leaky diode, I naught large. So, you can see here you have got a good diode I naught small, that means the barrier height in the case of n type material phi b n is large, which actually means phi m minus phi s is large, because then the bending is more, and this the bad one, large leakage current, large reverse current I naught, phi b n is small, which can be phi m minus phi s. The difference between the phi m and phi s is very small, or it can be even phi m may be lower than phi s. In fact, people or most of the time we see in literature a n type semiconductor with metal forms rectifying contact if phi m is greater than phi s. That is what we saw. But notice, if the difference becomes smaller and smaller, phi b n becomes smaller and smaller, it can become Ohm contact. That is what I want to say, because it is stretching it beyond certain point and telling you that phi m less than phi s becomes ohmic. It did not become less than phi s. Still, if this barrier keeps on reducing, that is, if this difference is reduced, that difference this is reduced. So, phi b n, okay, that becomes smaller and smaller. So, it becomes leaky. That is why I just deliberately brought this out. Now, let us just take a look at the other case. I can remove all this now, quickly go through the second case, n type semiconductor with. It is interesting to see what happens in an n type semiconductor with So, the second case now, what we are going to see is phi m less than phi f s. Now, you should be able to clearly draw this. I will draw this position somewhere here, because now the phi m is smaller, that means it is closer to this 0 level. Okay? That is the meaning of telling that E f m, that is the Fermi level. Now, it is an n type material, we are talking of phi m less than phi f s. Okay. This is extreme case of phi m minus phi m becoming less and less, ultimately it is less than phi f s itself. So, where will the Fermi level be? In the semiconductor, that is 0 level, no contact. Before contact is made, 0 level, phi s is larger than phi m. That means Fermi level there is much below. So, somewhere here, let me put it somewhere here, E f, and it is n type material. Let me just draw it slightly closer. Okay. I just show a small difference, and there is a conduction band. What matters is how much is that. Okay. That is n type material, then I have this E v. Now, what will be happen? When you join them together, thermal equilibrium, situation for this, what will happen? Thermal equilibrium situation will be, you will have electron transfer from here to here, Fermi level is above. The electron transfer from here to here means you are charging this portion negatively. Okay. It will become more n type near surface, and if it becomes more n type, it becomes difficult to transport these electrons into that portion. So, the neutral portion here, the energy band diagrams here will actually go up, difficult to if it negatively charged, when you take an electron near that, it gets repelled. That means, you have to spend more energy to take the electrons to that point. So, once it is negatively charged, the band diagram will move up. Okay, that is the key thing to understand. So, now when you form the contact here, we draw it bit up there, so that there is space. So, that is thermal equilibrium. Metal and then. Okay, for this case, phi s is larger than that. So, on the left hand side, that is not going to change. I will keep it as it is. And on the right hand side, Fermi level actually will go up, so energy levels will go up. So, over here it will be till that is matched there, EFM, EF. Okay. And this is EFM is same as EFM, both match. And what happens to the energy band diagram here? I will draw that parallel there. This entire thing has got shifted up, so that these two are matched, and the difference will be phi m minus phi s. Okay. So, when this goes up, what will happen here? Surface is actually more n type, because electrons have moved from here to here. Near the surface negative charge is there, meaning it is more number of electrons are there. So, this is slightly bent down, that is bent down. How much it bends down, of course, depends upon the potential difference there. So, that is like this. Correspondingly, you will have a bend here, and this difference is actually equal to that difference, band bending. Previous case also, that difference bending was phi m minus phi f s, which was built in potential. Here there is a small built in potential, because this difference we are showing is small. Now, under this situation, what is that is phi b n. See, phi b n is very bad, very small. Okay. If the difference is more here, it can even become negative there. This can bend below that. Okay. You can have a diagram which has a notch there. Okay. So, this does not have notch. The one example that I am showing here, there is no notch. So, what is the phi b n? That is the phi b n. That is the phi b n. Okay. And of course, that is phi b p. This is phi b n and is phi b p. Let us cannot talk about that right now. That is, sum of phi b n and phi b p is equal to band gap. If you look into this, if there is hole, that is the barrier for holes, because the energy of holes is higher when you go down. Okay. Now, what is the distribution of energy electrons now? The transport, how does it take place? Thermal equilibrium, let us plot like this. That is that. And this is a barrier. So many of them are above that barrier. You can immediately say that it is a very poor rectifier, ohmic contact. Okay. So, that is why this is the stretching, whatever we have been telling earlier, that is phi b n smaller and smaller, it becomes ohmic. So, it need not necessarily be phi m less than phi f s, it can still become ohmic, but when it is less than that, it is definitely ohmic. So, now here let me remove that portion now, because that is a barrier, and from here you have the electrons which have the energy. You can see total number of electrons here will be more than that. So, that is the thing. Now, what will you say? I do not have to draw any more diagram. It is very clear from here, so many electrons have the energy greater than that here, which can cross the barrier, and that number is matching with that here. All the electrons which are above that should be above that. The level has adjusted such that number crossing from left to right is matching, right is matching. Now, if I apply a potential to this, so what you have here is a slight accumulation layer, you can draw actually the diagram if that difference is too much. In fact, you should be able to draw that. This will come down below that, you will have virtually a diagram which will go like that. Okay? You can, I leave it to you as an exercise to see how the energy band diagram will be if this difference is even more. Okay? That you can do. Now, let us just see what happens when I apply this accumulation layer here. In fact, a small potential change will accumulate a lot of electrons there, because it is proportional to majority carrier into e to the power of V by V t. Majority carriers are large. So, you can, with a small change in voltage, there is a lot of difference here. Okay, that V is that whatever comes there. Now, if I forward bias, what happens? Which is forward bias? Make this plus, that minus. What will happen? If I make this plus, that minus. Okay. Forward bias. N type. What will happen? This will go up or down. We are having a potential which is plus minus, I am sorry, minus plus. When I am forward biasing, actually I am reducing that. Okay. You are changing the barrier, one of them you are moving out. Okay. In fact, what happens is now the electrons have moved from here to here, charging is negatively. If I make that plus on that side, okay. So, now this barrier is like this, I am sorry, like that, sorry, polarity is like that, because electrons have gone from metal to the semiconductor, that is the polarity. So, and because of that polarity, I have got this barrier like this. If I make a voltage like this, forward bias, what will happen to this? We are increasing that, that will go up, it will go up. Okay. So, in a forward bias, if you take a look at that, this whole diagram will actually be so that is the forward bias V. Okay, forward bias. Okay. Now, if that is the case, what will be the distribution now? Let me just put it down a little bit away. That is the forward bias voltage V by which it has gone up. Okay, let me put it here itself. V. Distribution here does not change. What was above this was matching with that originally. Now, this has gone up. So, this extra electrons, the electron energy has gone up there, the extra electrons now have energy to cross the barrier. They will give rise to current flow in this direction, electron flow in that direction, which gives a current flow metal to semiconductor. So, that is in that direction. Battery has to drive the current only in that direction. Okay. So, this lifting up has enabled additional electrons, large number of electrons are there, they can cross. If it pushes down, what happens? If this push down, okay, see here there is so much is there. So, this thing pushed down, see right now thermal equilibrium only these are crossing. If a reverse bias, okay, when I reverse bias it, this entire curve comes down. Okay, and the number that goes down, I do not know whether I can draw it on the same diagram. If you just try supposing a reverse bias, I think I will not draw it, I will just show that to you. This level will come down, that means this whole thing will come down depending upon how much reverse bias. The moment this level comes down, originally only this much were there, that was compensated by that. When this comes down, the number compensating goes disappears slowly. So, huge number of electrons can flow. That is why this I naught is large, and you get the IV characteristic like that going down. Let me just draw it separately here. So, the diode characteristics IV is current versus voltage. You can write it still I equal I naught V by V t minus 1, that is like this. You may have to go down there to get right up to that point. Very leaky diode, because huge, almost all of them will be able to cross once you bring this down. With a very small voltage, large current will flow through. So, this is a ohmic contact. Close to ohmic contact. So, there is no trick. If you want to make ohmic contact, choose a material whose phi m is smaller. Okay. It need not be less than phi of s. So long as it is closer and closer to that phi of s, you will have closer and closer to ohmic contact, otherwise rectifying. Now, let us go back to a p type substrate. We can quickly draw those diagrams now. P type. So, this where you can see in literature saying if phi m is greater than phi of s in n type substrate, it will become rectifying. Phi m less than phi of s in n type substrate, metal semiconductor contact becomes ohmic. But in between situation also it can become ohmic, because so long as the difference is small, it can be ohmic. If the difference is large, that is rectified. That is the point that I am trying to stress, because that is missed out to many places. Now, the p type substrate. P type. Metal contact on p type. Hereafter, it will be very easy for us to go through semiconductor. Okay. On the p type semiconductor, let us take the case where phi m is less than phi of s. Okay. When phi m is less than that, I will draw that 0 level. I will draw the 0 level corresponding to the semiconductor and the metal. That is 0 level. Phi m is less than phi of s. Very easy, because Fermi level in p type semiconductor is way down. See, if you see n type and p type, in a p type EF is below. So, for same metal if you put, you will have conditions different. Okay. So, this is the EF, that is phi m, and this is smaller than phi f s and a p type substrate. So, you will have this way down here, and p type semiconductor. So, E c is here close to valence band, and conduction band maybe here. Notice here, if it were n type, could be that this is closer to that, phi m and phi s may be matching. In fact, it turns out to be so. If you take aluminum metal, aluminum work function is about 4.1 phi m. Chi, electron affinity in silicon, is 4.05. Gallium arsenide also about that. So, phi m s is practically 0. Phi m minus chi is very small. So, if you take n type substrate, if the conduction EF is close to conduction band, phi m minus chi s may be very small. you should get ohmic ideally. If you take p type substrate, that extra difference is there. This is almost matching there. If it is aluminum and if it is semiconductor, that extra difference is there. Now, let us see what would happen. So, this is the semiconductor, this is the metal. I bring them together, thermal equilibrium, write down here. So, you have got these two situations, metal, p type semiconductor. Okay. So, you have got nothing is going to happen again here, nothing is going to happen here, because no potential changes will take place there in the metal. So, I will retain that right there, that is here. Since Fermi level is below, the electrons which have higher energy here can cross over to that till they are equalized. So, the same thing happens here, you have this EF, okay. EF becomes same both cases. Electron transfer takes place from metal to the semiconductor till the Fermi levels are equalized, because electrons are at a higher energy compared to this semiconductor. EF higher means higher energies are there. Okay. So, now what will you do for this portion? Electrons have got transferred from here to here, that means this has become negatively charged. It has become negatively charged means a p type semiconductor, if you push electrons into that, that will neutralize the holes. Okay. So, whatever holes are there are removed, the portion becomes negatively charged, you get a depletion layer. So, when because of the transfer of this, you will have a depletion layer there, which are negative charges, charged negatively. See, otherwise what you have is like that, you transport an electron onto that, that is removed, negatively charged. Okay. So, now here what is the energy band diagram will you draw now? Once you draw the Fermi level, it is very easy. You know that this portion is actually, this is flat and that is the valence band, comes flat like this, and this is negatively charged, which means there is electric field in that direction. Electrons have moved over there, so there is electric field from left to right, and okay. See, you can see very easily, you have got the electrons transferred onto that, okay, more negatively charged. So, the entire energy level has gone up till the Fermi level matches with that. Repeat again, electrons have got transferred there, difficult to bring electrons closer to that point, the energy of those portions goes up, energy level. So, this has gone up, and okay. Now, here that will bend down like this, because electrons have gone in there, it is a depleted layer or less p type, conduction band valence band gap increases. Okay. When you say depleted, it is less p type. There are mobile electron holes are there, that becomes smaller and smaller as you move away. It may not be 0, there will be some holes will be there, it is very small. So, this becomes less p type, and here conduction band like this. Now, you talk about these electrons, there will be very small numbers here, okay. And the one charge carriers in the semiconductor are not the minority electrons, these holes, that will come like this. They are mobile holes which have energies above that. Okay. And in the metal also you can talk of holes, in the sense, see, you have got the electrons here which are which are coming like this, you have got the electrons there. What is this due to? Where has it come from? From here. 0 if you go down at very low temperature, most of the electrons will be below that. Now, as at room temperature, the electrons have gained energy and gone up, and they have to come from here. So, there are actually vacancies which are present here, okay, which actually are maximum here. If you go down, you will have similar distribution for the holes. What is hole? After all, it is absence of electrons which have gone up from there. So, these are vacancies which can interact with this. So, instead of talking of electron transport there, you can talk of hole transport here. They are actually matched with energy from bottom. These levels are tipped at thermal equilibrium. Okay? So, the holes which are having that can cross this barrier. This is the barrier. What is this actually? Phi Vp, and this is actually phi Bn. We do not have to worry about phi Bn now, because this is small and this is up to that point. Okay, now, we have to see what happens to this energy band diagram. Okay. So, you have got those holes and those holes just crossing the barrier. The diagram here I have not shown that, but you have got some of the descriptions which come up later. Okay. So, you have got some of these holes which have I am sorry, here this is a barrier. So, all these holes, redraw that. Okay. All these holes have energy greater than that barrier. There is messed up a bit, I just redraw that here, and here all these holes above that can cross, all these can cross, that is I naught. How many holes can cross from here to here depends upon this barrier. More it is, that becomes, that is exactly what we are talking for electrons, for holes. Only instead of talking the barrier up there, you talk of the barrier down here. Okay. Now, when you forward bias this or reverse bias this, what happens? This is not going to change. This number here is not going to change. All that number that will be changing will be this. Okay. So, if I actually apply a plus voltage here, what would happen? I make the metal positive with respect to the p type substrate. What would happen to the barrier? You have to just see, this is the built in potential here. Whatever bending was there, that is a built in potential, and the polarity is plus minus built in potential. When I put a polarity here V here, I am not telling you whether it is VR or V, I am just telling you V now. That polarity is aiding on to the built in potential. Built in potential is plus here, minus here. When the energy band diagram goes down, that is positive, positive, negative here. If I apply V, that is adding on to that. If it adds on to that, what happens to the energy band diagram? This whole thing will go up. This will actually go up like this, okay, and this will go up like that. Okay. So, you have the energy band diagram gone up. When it goes up, this will go up there, this will go up there, that is the minority carrier, and this actually is not changing. So, current due to electrons will be there, small current because of this minority carrier, okay, which will be very, very small, like the p-n junction minority carrier current, that will be there rolling down, because you have taken it up and this distribution goes up here. Okay. I think we are running out of time today, so I will just go back to this particular IV characteristics of this p type substrate tomorrow or next lecture. So, the idea here is electron is not contributing when it goes up, because the electron concentration is small, but when this goes up, what happens to the hole concentration which we are crossing from here to here? That is going up now. So, none of these holes have enough energy. This is a barrier for holes, they have less barrier, more barrier, they are not able to cross. But this number crossing from here to here remains the same thing. So, you will have now current due to these holes which are crossing from here to here. Okay. You will have that is from here to here, holes crossing from metal to semiconductor. So, you will have current due to them like that, and that number will be small, if this quantity is small. That quantity will be small if this is large. So, here again, so this will be forward bias or reverse bias. Reverse bias, you are blocking, you are not letting these holes to cross, you are discouraging them from opposing the current flow here. So, you are removing them out of competition with these holes. So, once this is removed out of competition, only this is there and that is constant. If we keep on increasing the reverse voltage, once this goes out, this goes on increasing, and at the end you will have I naught, which is decided again phi b n. I will get back to this tomorrow, then sum up that may take me for 10 minutes or so, then we will see whether what we are talking is real. In real practical structures, it may be slightly different. That we will take up tomorrow, next lecture. Thank you. So, we will see.